evaluated our proposed prototypical network in a few-shot learning task composed of instruments that we had never seen before training. So we took all of the METLI-DB dataset, which had we took all of the METLI-DB and METLI-DB 2.0 dataset, and we kept 63 instruments for training and 24 for testing. So the 24 instruments that were seen during testing were never seen during training. Those are completely new instruments, and we're sort of like trying to like evaluate how well our model does on instruments that it's never seen before. As for the data pipeline or how we like trained our model, we removed all silent regions from tracks. So we had like a track which was like a solo isolated performance of a single instrument, and we removed all the silent regions. We split the data into 1 second chunks, so our model is able to classify on a second by second basis. And we sample them to 16 kilohertz. And for each one of those audio chunks, we take a 128 beam spectrogram, and that's what we use as input for a convolutional neural net that's gonna, at the end, produce a 10,024 dimensional vector. And that's what we do the distance calculations with. So this 10,024 dimensional vector here is one dot that you see projected onto the space. So we trained both the baseline model, which is a model that does not use hierarchy. So the baseline model would be this, and our proposed model would be the one that incorporates several levels of hierarchy. And we trained each of them on 12-way 4-shot classification task. So every step, every like training step, we would grab 12 instruments from the 63 instruments that we have. So we have the bank of 63 instruments. We pick 12 of those randomly, and we grab 4 examples for each of those instruments. And that's a classification task. So the goal, and we pick 4 of them for training, and then 12 per instrument for computing the loss. So those are like the query examples. The 12 examples are the query examples, and the 4 examples are the support examples. So each of those training steps, you're sort of like doing a 12 classification task. So you're going to have 12 instruments sort of on this embedding space each training step, but it's going to be 12 different instruments every time. So that's how it's different from like a regular supervised classification task. And we do the same thing for evaluation. We train for 60,000 steps, and we evaluate on 100 steps. Still 12-way, which means that we grab, out of those 24 instruments that we have for testing, we just grab 12. And then we're going to vary the number of support examples, the number of labeled examples that we do give it, because we do want to see how that behaves in our experiments. So to talk a little bit about metrics, we're going to use the F1 score for classification performance. So how good is it at classifying the instruments? But we're also going to keep track of the severity of mistakes. So you can consider a really severe mistake, for example, if the real answer was a Puerto Rican cuatro, and a better mistake or a good mistake would be to confuse a Puerto Rican cuatro for another string instrument. Because sometimes I'll listen to an electric, or like I'll listen to a Puerto Rican cuatro and maybe go like, oh, that's a 12-string guitar, and you know, it's a reasonable confusion because they sound really similar. A worse mistake would be confusing the Puerto Rican cuatro for a flute, and we're trying to measure that because models that make less severe mistakes are probably more likely to be trusted by users of the interface if they see that the sort of like mistakes that the model makes make sense in a way. So here's some results about our experiments. One thing that we tried is different levels of hierarchy. We tried, so here h equals 0 would be no hierarchy at all, so the baseline. H equals 1 would mean 2 levels. You have the base level and then 1 level hierarchical level on top. 2 levels would mean the base level and then 2 levels on top, and so on and so forth. And what we found was that the 2-level model, so h equals 1, is the one that did the best. which felt a little contradictory at the beginning because we expected like higher trees or like more hierarchy to actually lead to better improvements in performance. But there's a problem with that. There's a problem with that when we have the few shot learning scenario. Like I mentioned, we're only grabbing 12 instruments at a time during training. We're not grabbing all 63 of them. And this is sort of what happens when you only grab a subset of the hierarchy. So here you have a two-level hierarchy. And the problem here is that at this really specific level, where you have plucked, bowed, woodwinds, and reed, there's no meaningful groupings. There's nothing to put together. You're going to grab all the examples for the guitar and then nothing next to it. So all the plucked instrument prototypes are going to be equal to the guitar prototypes. So there's no meaningful grouping in that level, which means that we don't have anything to learn there. The loss for this level is going to be equal to the loss for just classifying guitars. And the loss for bowed string instruments is going to be equal to the loss of just violins. So if you get rid of that intermediary level and you just leave the meaningful level, you're going to find out that you find a lot more meaningful groupings. So you have the guitar and the violin here. They're both string instruments, and you have two prototypes to aggregate now. And that actually will like lead to the model learning this sort of hierarchical relationship. So you have two options. You cut the tree to a few number of levels if you only have a couple of examples, if you only have a couple of instruments. But another option would just be to increase the number of instruments that you include during training, which is something that we could explore in future work. Which is now that you have more instruments at the bottom level, you have meaningful groupings. So the plugged instruments, there's the Puerto Rican cuatro and the guitarra, those can be aggregated together, and then the viola and the viola and the violin, violin, Spanish, English, can be aggregated together, and you can sort of like keep doing that as you go up the tree. So deeper trees are better if you have more instruments, but because we only had 12, it was usually the case that we ended up like this. So this kind of method did better. Another experiment that we did was just the number of support examples. So this is the number of examples that the user has to find to provide to the system when they want to classify something. So if I want to learn a new instrument, let's say I have a cuica, and I want the model to learn what a cuica sounds like, I'm gonna give it a number of support examples. So we tried here just giving it one example for the instrument, then 4 examples, then 8 examples, and then 16 examples. And as the number of support examples increases, so does the amount of effort that a human has to make to use the system. And naturally, we found that as you provide more support examples, the model performs better, and it also improves more when compared to the baseline. And this chart on the right is the mistake severity, so how severe are mistakes. And here, lower is better. And you'll find that our model makes less severe mistakes, or is less likely to confuse a guitar for a flute than the baseline model. Some of the more interesting, one of the more interesting experiments that we did is what happens if you just tell the model to organize randomly. What if you just made a random hierarchy that did not really make sense? How would the model behave if you just randomized everything and just aggregated random instruments? Okay, both flute and guitar are string instruments, put them together. That's sort of what we tried here. And the way we tried it was we made 10 different random hierarchies and trained a model on each of them. And we just picked the best performing one and the worst performing one, and that's what we're showing you here. So here's the baseline. This is the one we propose. This is our model. This is the best random hierarchy, and this is the worst performing random hierarchy. So it was kind of a surprise that we found out that the best performing random hierarchy, just like random combinations of instruments, did just as well as our proposed hierarchy. And the worst one did worse than the baseline. So there's kind of like mixed conclusion to get out of this, but sort of what we found was the choice of hierarchy was not arbitrary, so you can't just pick a random hierarchy and that's assume that it's going to work. But there are other meaningful structures. There's other ways to organize instruments that we could use for our advantage. And this is actually something that I want to explore in future work. And maybe it's a good idea because our system doesn't actually incorporate like a very specific organization or hierarchical organization into the architecture of the model, but rather just does it by taking the average of different things together, creating those prototypes of prototypes. We can use multiple hierarchies at the same time. So maybe we could organize instruments by sound production, which is what we're doing here, but at the same time we could organize them by pitch. So maybe we could put all of the alto range instruments together and all of the tenor instruments together and organize them like that, and see if we can learn something new from there. Other ways of organizing, like the genre that they're usually used in. And I can think of like other ways of organizing instruments, and the idea is that we can take advantage of them at the same time, hopefully, to get even better performance. The next to last experiment was so how do we weigh the different levels? Do we give the most priority to the lowest level, or do we give the most priority to the coarsest level? So do we let this is related to this over here. So what we tried was varying this alpha parameter. So here, negative values of alpha would give more priority to the coarse level. So like, strings and winds and percussion, and a positive value of alpha would give more priority to the lowest level, like cuatro or guitar, violin, flute, etc. Because the task that we care about is actually the lower level, you'll find out that what does best is actually, as you increase positive values of alpha, you get a better performance. And we found that we had the best performance whenever alpha was equal to 1, which means that there's like a significant like exponential decrease as you go up the class hierarchy. And we also tried an approach where was this no multi-level. So you know how we treated everything as a separate task for the different levels of the hierarchy. So we got rid of that and we just put everything flat on the same level. And it was kind of a binary classification thing now, where the thing could be guitar and it could be strings at the same time, and it could be plugged at the same time, and it could be allowed to also predict violin at the same time. And that actually caused a degradation in classification performance. And the reason for this is that prototypical networks don't really lend themselves to binary classification. And the reason for that is that because it's like a distance-based classification, you can't be close to something. You're sort of like having the loss sort of like pulling things in multiple directions. So if you have something that is plugged and also a guitar here, and you have a new example here that you're trying to learn as a guitar, you sort of have both of them pulling you in different directions if you have this sort of like flat binary classification approach. And the last experiment we did was we just looked at each individual classification performance for each instrument, and we found that our model does better at classifying instruments for a wider variety of instruments. So 75% of the instrument classes in our test dataset, our model was better at identifying when compared to the baseline, which sort of like was the whole point of like this research work, was being able to classify a wider variety of instruments that our model has never seen before. So just to wrap this project up, I talked about a extension to prototypical networks for few-shot learning that incorporates a hierarchy so that we can use it with musical instruments. Our model does much better at classifying instruments when compared to the non-hierarchical baseline. also makes less severe mistakes, which it means that it's less likely to confuse a guitar for a flute, and more likely to confuse a guitar for another stringed instrument, like a ukulele.